So at the start of my presentation, I wanted to just briefly give an overview of the process that I'm going to follow. So I'm going to introduce the Bose-Einstein Condensate, the phenomenon at the core of the atom laser and the properties associated with this. I will then link this to optical lasers through the matter wave analog. I will then introduce a bright atom laser in a weak field and the limitations associated with this. I will then introduce the ultrabright laser using strong fields, talk about the applications of this and the future developments of the field. We begin this presentation at the core of the atomic laser, and that is the discovery of a fifth form of matter, the Bose-Einstein Condensate. At high temperatures, a cloud of ideal gas particles can be pictured as individual particles moving at high speeds with randomized directions. This is known as the classical region. As the temperature is lowered to a couple of Kelvin, the particles move at slower speeds and the wave-particle duality of the gas atoms becomes important as we enter the quantum mechanical region. Here, the particles are represented as thermal wave packets and their width is represented by the de Broglie wavelength shown here. From this inverse relationship, we can see that as the temperature is lowered further, the wave packets will stretch out. At and below a certain temperature, known as the critical temperature, the particles begin to overlap and their identities become entangled with each other. As this overlapping increases and the temperature is lowered, the particles all lose their individuality and they begin to be represented by one wave function. They become a giant matter wave. This is known as the Bose-Einstein Condensate. We could also picture this system as having all the atoms sink into the lowest energy state. Therefore, they are also referred to as cold atoms. The important thing to note is under the Pauli exclusion principle, fermions cannot occupy the same state. Therefore, this phenomenon is only achieved with bosonic particles. So, how do we actually form a Bose-Einstein condensate? Well, the temperature required is around 1/1,000,000th of a degree of Kelvin. We can use laser cooling to reduce the temperature to around 100 millikelvins. And in this process, we basically fire pulses of laser radiation at these atoms. The atoms scatter these radiation, causing a recoil effect opposing their motion. This reduces their speed, their momentum, and hence their kinetic energy. This in turn reduces the internal energy of the entire system, lowering the temperature. However, in order to achieve the temperatures required for Bose-Einstein condensation, we need to do two things. Firstly, we need to trap the atoms. So how we trap them is we utilize the fact that atoms have individual magnetic dipole moments. This will mean that they will interact and feel a force in the presence of a magnetic field. Now, if there are multiple fields coming from multiple directions, the atoms feel a force from all directions, creating a potential well that traps them in space. Once they are trapped, we can use a process known as evaporative cooling. Now, here it is important to note that in the presence of a magnetic field, the magnetic dipole moment can orientate itself in more than one direction, and each direction has a characterized energy level. These are known as the Zeeman levels, and they are represented by the spin quantum number mf. As shown here, this means that there is an unbound state below the trapped state. The process of evaporative cooling is therefore as follows. Higher frequency radio frequency photons of similar energy to the gaps in between these Zeeman levels causes the hot atoms at the corners of the potential well to flip spin states and therefore evaporate off down the potential hill. The system then rethermalizes this energy and the process is repeated, lowering the frequency until the hot atoms have all been evaporated off, and this allows us to reach the critical temperature. The important point to note is that the Bose-Einstein condensation can only be informed inside a potential well. And what this means is that the Bose-Einstein condensate is effectively trapped, it is localized in space. So, utilizing this aforementioned method in the last slide, in 1995 the first Bose-Einstein condensates were achieved using sodium atoms, first by a research group at Boulder, and then a few months later by a group at MIT, run by Wolfgang Ketterle. A year later, in 1996, the same group ran a test which displayed a fascinating property of Bose-Einstein condensates. They showed that all atoms inside the condensate were coherent. So how they did this is they took a Bose-Einstein condensate and subjected it to an intense pulse of radiation causing the state to split into two. The trap was then turned off and the states fell under gravity, before expanding and overlapping. At this point, the group observed a clear constructive and destructive interference pattern. Now, this is representative of two coherent waves interacting, as if the waves are incoherent, they'll be a muddled mess. However, because they're coherent, when they're interactions, we get these clear signs of constructive and destructive interference as seen in the picture. So what this truly showed is that each Bose-Einstein condensate was acting as a giant matter wave. In other words, all atoms inside this condensate were moving in the same mode. They were moving at the same frequency, and therefore they were all coherent. And so the key thing to note is that these trapped Bose-Einstein condensates formed in potential wells and localized in space are coherent. So this idea of coherent particles trapped and localized should ring bells in regard to the idea of optical lasers. An optical laser is created through stimulated emission of coherent photons from excited electrons resonant with incident radiation. These photons then travel inside a trapped optical cavity, further amplifying this effect until there are a large number of photons inside. These coherent photons are then outcoupled from the trapped cavity by a partially transmitting wall on one side. This, in effect, allows trapped coherent photons to exit and create an intense, freely propagating coherent beam of light, a laser. An atom laser can be thought of as a matter wave analog to this idea of an optical laser. But instead of coherent photons, we have coherent atoms trapped inside a potential well. The key question is then, how do we get these atoms from the trapped state into a freely propagating state? And the answer is, we use processes known as output coupling mechanisms. The first output coupling mechanisms were realized through the introduction of weak fields to the trapping potentials, causing bound states to be outputted into freely propagating states. These traps and state-changing output coupling mechanisms are displayed here. However, in the interest of time, I'm going to focus on the atom laser produced by the group in Munich in 1998. This is because they produced the atom laser that was the brightest, and they serve as a perfect case study in which to introduce limitations with bright atom lasers and how, in fact, the group in Greece were able to use this limitation as a strength and achieve an ultra-bright atom laser. To start, for clarity, let's define what we mean by bright atom laser. Bright refers to a high flux laser, which in other words means a high number of atoms propagating in the beam. The more atoms we are able to outcouple from the trapped state into the untrapped state, the brighter the laser. So what the team in Munich did is they took an 87 rubidium atom, which is a quantum number f equal to 2. For completeness, this quantum number is a result of the coupling of the net orbital angular momentum and the net nuclear spin inside the atom. However, what's important is f equal to 2 means that in the presence of a magnetic field, the orbital dipole moment can align itself in 5 directions, characterized by mf equals -2 to mf equals +2. Therefore, in the presence of a magnetic trap, 5 hyperfine Zeeman levels are produced, as shown. The result is that a trap forms in the mf+2 state, shown in the figure. Therefore, the group loaded atoms into this trap and used evaporative cooling in order to form the Bose-Einstein condensate in the mf+2 state. Now, atoms, unlike photons, have mass. Therefore, they feel the effect of gravity. What this means is that the potential well is deformed in the direction down from the center of the Bose-Einstein condensate, which here is defined as the y direction. The xz plane can be pictured as the horizontal plane through the middle of the condensate, and here the wells would be symmetric and without this tilt. A weak radio frequency field is then switched on, and this introduces pulses of RF radiation that stimulate spin flips from the mf+2 state to the mf equals 0 state via the mf+1 state as shown schematically to the right. Due to the deformation under gravity, the particles move down the potential only in the y direction, and therefore they accelerate out below the condensate under gravity, creating a freely propagating laser. Through this method, the group in Munich were able to achieve a flux which they estimated as 5 × 10⁶ atoms per second from initial 1 × 10⁻⁶ 9 atoms loaded into the trap. The atom laser produced by the Munich group had two key limitations associated with the state-changing output mechanism that greatly reduced the flux it was able to produce. Firstly, the atoms that are outcoupled into the propagating beam come from within the condensate. What this refers to is that the atoms that are removed have to travel through the rest of the condensate below. The remaining atoms within therefore act as a thin lens, spreading the beam and greatly reducing its focus point. This is known as the matter wave lens effect. As shown in the two diagrams to the left, this effect is greatest when the higher energy atoms are removed from the system first, and hence feel the greatest interaction with the rest of the condensate below. This is an issue, as it is hard to focus the frequency of the RF field to the bottom of the condensate, and thus the RF field is simply swept from a high to a low frequency in order to achieve both the evaporative cooling and the lasation. Achieving a highly collimated beam is a crucial property of a laser. Therefore, the divergence of the atoms under the matter wave lens effect lowers the number of atoms that can enter the effective collimated beam, thus limiting the flux. Secondly, the weak RF field has a magnetic field component as with any other form of electromagnetic radiation. In the Munich group, the atom laser field can be described as a weak coupling field. This means the RF field hardly interacts with the magnetic field. The flux can be improved by increasing the intensity of the field, the RF field, meaning more atoms are outputted and flow per second. However, as intensity increases, the strength of the RF field also has to increase. This means that the RF field begins to interact with the magnetic trapping field. At a certain point, the fields are coupled together so strongly that they cause the hyperfine Zeeman levels of the potential wells to overlap, as shown schematically to the right. Due to avoided crossings in the adiabatic region, new dress potentials are formed. As shown in the furthest image to the right, this creates a new potential well trap in the MF equal to -2 state. The new traps are known as the bound states, as the atoms can no longer be outcoupled using state-changing methods. They are bound in this lowest potential well. This is a crucial limitation to the atomic flux of any state-changing coupling mechanism. Now, in the last slide, we saw that a strong RF field causes the creation of dress potentials, forming a new trap in the MF-2 Zeeman level of a rubidium atom trapped in a magnetic field. And what we saw was that these bound states greatly limited the flux the laser was able to achieve. However, in 2014, a research group from the Institute of Electronic Structure and Lasers in Greece decided to utilize these bound states in order to achieve an ultrabright atom laser, and in doing so, they improved on the flux achieved by the Munich group by 14 times. How they achieved this was by intentionally using a strong RF field in order to couple the hyperfine Zeeman levels of the rubidium atoms, therefore creating the dress potential trap in the MF-2 level. This is shown in the diagram to the right. They loaded rubidium atoms into the MF+2 state and ramped down the frequency of the strong RF field. This resulted in evaporated cooling and the Bose-Einstein condensate forming in the MF-2 state. In the diagram, the arrows represent the point at which the strong magnetic component of the RF field is resonant with the magnetic trapping field. In other words, this is the point at which the two coupled potentials overlap and the avoided crossings form the new trapping well. Here, the diagram is depicted at the moment this resonant point is level with the maximum energy point of the Bose-Einstein condensate in the y direction. As before, the gravitational field pulls the atoms in the negative y direction, causing the trap to tilt. Now here, this can be thought of as the point directly before lasation begins. As the frequency is ramped down further, the resonant point between the fields lowers in energy. Effectively, the arrows depicted move inwards. We can imagine that as the arrows move inwards, they effectively push the Zeeman line upwards, reducing the depth of the trap. If we picture the atoms inside this trap as peas, As this happens, the atoms slowly spill out of the condensate in a negative y direction, directly below the condensate. Therefore, as the RF frequency is ramped down further and further, the atoms lower in the trap spill out and accelerate down under gravity, until the RF frequency is ramped down to a point such that the trap is non-existent. In this way, all the atoms in the Bose-Einstein condensate leave the potential trap. Therefore, the group were able to achieve the maximum flux possible. So, as mentioned in the slide before, the Greece group were able to achieve an ultra-bright atom laser that is depicted in the figure to the right. They recorded an initial atomic flux of 7.4 times 10 to the 7 atoms per second. This shows a 14-fold increase from the flux achieved by the Munich group. And after falling for around 2 millimeters, the flux dropped down to 5 times 10 to the 7 atoms per second, which is still a 10-fold increase. These results are all depicted in the graph to the right. The reason for this high flux was the vast improvements on the flux limiting processes associated with the state-changing output coupling mechanisms previously mentioned. In regards to the matter wave lens effect, all of the atoms are removed at the corners of the potential well, where the tilt allows them to fall out under gravity. Therefore, this effect of the matter wave lensing with these atoms below the condensate causing a dispersion is virtually non-existent. Furthermore, in regard to the bound states, all the atoms trapped transition into the laser. The flux is simply a rate of how fast the RF frequency is ramped down. There are no bound states. In fact, there is a bound state, but they've utilized it in order to create the laser. They've turned this negative into the positive, which has allowed them to create ultra-bright atom lasers. So now I'm going to move on to the applications of atom lasers and why a high flux is desirable. So the first application I'm going to discuss is atom holography. This is analogous to optical holography, in which information about an object is embedded into a 3D diffraction grating, a hologram, and then a beam of light shone through this diffraction grating reforms the image on a photographic plate. Atom holography is the same concept, however, it employs coherent atomic waves, of which these de Broglie wavelengths of the atomic waves is around 10,000 times smaller than the wavelength of light. What this means is that atomic waves are much more sensitive to the intricate details embedded in the diffraction grating, and therefore they can be used in order to create holographic images with greater resolution. An example of this concept is displayed in the figure to the right, where the atomic beam is used to project a nanoscale pattern of an integrated circuit onto a semiconductor. A high flux is desired as the more atoms flowing per second, the more atoms there will be diffracting through the grating, creating a clearer and more intense image. The second application I'm going to discuss is atom interferometry. Here, a coherent beam of atoms, an atomic laser, is split into two and sent down different paths. When the beams recombine, we see an interference pattern, just like the Kettle group did in 1996. The interference pattern shown is highly sensitive to the phase difference between the atomic beams that have taken two different paths to get there. If we subject the paths to different physical conditions, we can conduct intimate analysis of how atoms behave in magnetic, electric, and gravitational fields. This concept has been used thoroughly in optical experiments where optical interferometers have been used. An example of this is shown to the right, and it's a Michelson interferometer which was used to investigate the existence of a medium in which light propagated through. This was known as the ether. So the example experiments I have listed here are, firstly, we can analyze the existence of dark matter. So dark matter, which is thought to account for roughly 80% of the matter in the universe, however, we're not able to see it. Dark matter may in fact form in clumps, and so it may vary in its density as the Earth moves throughout its orbit. This variation may be detectable as fluctuations in how fast atoms fall towards the Earth in atom interferometers, and we can place these at different locations and test this. Finally, we could analyze the polarizability of atoms by subjecting two atomic streams into different electric fields with varying strengths. We will then be able to measure from the interference differences how much the positive and negative charges within the atoms have shifted to align themselves with the fields. So in regards to the future of ultra-bright atom lasers, there are two core areas of concern. The first is increasing the flux even further. Now, as we've shown, we are able to have all of the atoms from the condensate moved into the freely propagating laser. However, in order to achieve a flux even further, we need to create larger condensates and therefore have more atoms available to be moved into the laser, having more flux. Furthermore, similar to this, faster frequency downramping rates will allow us to output atoms from trapped to untrapped states at much faster speeds, greatly increasing the flux. The second area of concern is achieving a fully continuous beam. Now, atom lasers currently operate in a quasi-continuous manner, and what this means is that once the condensate is empty, the atomic laser stops flowing. And what we need to do to get a truly continuous beam is we need atomic pumping. Now, this is analogous to optical pumping, allowing lasers to have long-length continuous beams. So what this does is it allows the Bose-Einstein condensate to be replenished while simultaneously the atoms in the condensate being released. This has been shown by a group in 2008 which used 87 rubidium atoms, and they created two condensates simultaneously, the top state acting as a source and the bottom state acting as the lasing mode. However, there's still limitations to this, as of course once the source is emptied, the lasing mode itself is then emptied. And so there's still work to do in regard to obtaining a purely and truly continuous atom laser.